Today let's talk about partial derivatives. A partial derivative is a derivative where some variables are held constant. Let's think about a function with only one variable, where we have f of x is equal to x squared. We can find its derivative using the power rule. That gives us 2x. But what if we have a function with two variables? Say we have a function f of y and x is equal to x squared plus y squared. We can find the partial derivative with respect to x, and that's going to give us 2x plus 0. That's because we're treating the y as a constant, and the derivative of a constant is just 0. So our final answer is just 2x. Same if we're taking the partial derivative with respect to y. That's going to give us 0 plus 2y. This time, our x squared is being treated as a constant, and taking the partial derivative with respect to y will make that 0. So our final answer is 2y. Let's talk quickly about notation. So you just saw me using this sort of notation to denote the partial derivative with respect to y. But you can also write this like this. This little backward 6 symbol is called a del, and you'd read this as del f over del x. So a second ago I told you that a partial derivative is where we hold some variables constant. What do we mean by that? Well, let's take this cylinder for example, the volume of which is equal to pi r squared times h, where r is the radius and h is the height. We can write this as a function with two variables, the two variables being radius and height. Let's take the partial derivative with respect to r. So we'll have del f del r will be equal to 2 pi r times h. You see, we just took the derivative of the r variable and we left the h alone. Now the h didn't go to 0 because this whole thing is a product. If it were, say, pi r squared plus h, then it would go to 0. But here, h was just brought down. Nothing changed. So we have our partial derivative with respect to radius. What is this information telling us? It's saying that if the radius of this cylinder changes by some amount, the volume changes by 2 pi r times height. Now let's find the partial derivative with respect to h. So that's going to give us del f del h, and that's going to give us pi r squared times 1, because h is to the first power, and by the power rule we would get 1 times h to the 1 minus 1 power, which gives us 1 times h to the 0 power, which leaves us with just 1. So our partial derivative with respect to h is just pi r squared. And this tells us that if the height of the cylinder changes by any amount, the volume of that cylinder will change by pi r squared. Next, let's look at this rectangular prism and its surface area. The surface includes a top and bottom with areas of L squared each, and 4 side areas with area HL. So we can write that as a function with 2 variables, LH, 2L squared plus 4HL. Let's find the partial derivative with respect to L. So we have del F over del L. That's going to give us, by the power rule, 4L plus 4H. You see again, the H didn't go to 0, even though it's a constant, because we have an L being multiplied to it. Now let's find the partial derivative with respect to H. So we have del F, del H. That gives us 0 plus 4L, or just 4L. You see now this term, with just an L in it, went to 0, and this term, the derivative of h to the first power is just 1, and this L that was being multiplied to that h got to continue on. So our final answer is 4L for the partial derivative with respect to h. Here we have a cube where each side has a length of x, and it has a prism cut out of it. This can be written as a function with 3 variables, x, L, h. That's equal to x cubed minus L squared h. Let's start by finding the partial derivative with respect to x. So we have del f, del x will give us 3x squared minus 0. There's no x in this term, it's just constant, so it goes to 0. 0. Now let's go ahead and find the partial derivative with respect to L. So we have del f, del L. That'll give us 0 minus 2L times h, or just negative 2LH. There is no L in this term, so this went to 0. Last, let's find the partial derivative with respect to h. This will give us 0 minus L squared times 1, or just negative L squared. Again, no h in this term, so it goes to 0. And the derivative of a constant is just 1, so we get negative L squared. Let's do a hard one. What if we had f of x and y is equal to y cubed times sine of x plus x squared times tangent of y? Let's first find the partial derivative with respect to x. That's going to give us y cubed. The derivative of sine of x is going to be cosine of x, plus the derivative of x squared, that's 2x, tangent of y. You see both terms had an x in them, so nothing went to 0. Now let's find the partial derivative with respect to y. So that's going to give us Let's see, the derivative of y cubed, that's 3y squared sine x plus x squared, and the derivative of tangent of y, that's going to give us secant squared of y. Those are our two answers. Let's do one more example. Let's say we have a function with three variables, x, y, and z, and that function is x to the fourth power minus 3 times x times y times z. Let's first find the partial derivative with respect to x. That's going to give us 4x cubed by the power rule minus 3yz. See, we took the derivative of this x, and that derivative is just 1. So we're left with 3 times y times z. Next, let's find the partial derivative with respect to y. That's going to give us 0 minus 3x times z, or just negative 3xz. This term went to 0 because there's no y's in there. And we took the derivative of this y, which is just 1. So we're left with negative 3xz. Last, let's find the partial derivative with respect to z. And that'll give us 0 minus 3xy, or just negative 3xy. Again, this term went to 0, and the derivative of this z is just 1. So we're left with negative 3xy. We just went over partial derivatives. I hope you learned something, and thank you for watching.